record that. Okay, so the length here is 5 meters. And now the pendulum is here, and then you're going to let it go swing. So it goes from potential energy to kinetic to potential to kinetic to potential, and so forth and so on. My point is that if you want to find that delta H, okay, so that delta H, it's going to be the length of the pendulum. You see that length here, which is 5 minus this here, right? So I'm going to call that D. So that delta H will be the length of the pendulum minus this. And this is the adjacent side here. So it's going to be 5 cosine 53. So you can factor out the 5. Okay. So you don't get stuck with that. It's just a very easy trigonometry. Okay, so again, in the pendulum, we start with potential energy, and then potential, some will be lost, and then you go to kinetic energy, and then at the bottom, everything is kinetic, but the level here does not change unless there is some air resistance. So in that case, you're going to lose some energy. Okay, so just the parentheses just to make sure you get this right. Again, very tired today, so be nice. Okay, so we stopped here. Conservation of mechanical energy. So if there is no air resistance, if there is no frictional force, you're going to have the total potential energy plus the total kinetic energy before equals total kinetic energy before, after plus total potential energy after, right? So we did all that. I hope you save your memory. Okay, so in that case, this is interesting because in that case, it has no potential energy to begin with, no kinetic energy to begin with, but you have work done. Okay, so the system is getting work done by burning fuel. Okay, so when you burn fuel, it's going to apply a non-conservative force. Okay, so there is no potential energy, but we already did this one, just to remind you. So the system to begin with didn't have any energy, okay, so it was empty, it's like a reservoir, and all of a sudden, you're going to burn fuel, so you're going to add energy to the system. Okay, that energy comes from chemical potential energy, right? It's like there is an explosion, so you're going to break the bounds, right? You're going to release some energy. Okay, so you go from this work done, which was 425 joule, and that same level of energy is going to turn into some potential energy and some kinetic energy, but the level stays the same. So it was 425 joule. Okay, so it's nice to visualize energy like a reservoir. So you have 425 to begin with. Some of it will go to potential energy, and some of it will go to kinetic energy. And you see here, I cannot cancel the mass. Like if it's in free fall, I can, and here I can't. Okay, so we did that last time. Okay, so we did this one. The answer was 61. So now in the potential energy, we can also include elastic potential energy. So energy that you store in a spring. Okay, and we did the math already, right? So the energy that you store in a spring by doing work will be equals to 1/2 K is a spring constant times x squared, and x is how much it's being squeezed or stretched. So it's a conservative force as well. So for example, if this one is going to fall, it has potential energy, kinetic energy. Kinetic goes to spring, elastic, and then elastic goes to kinetic, kinetic goes to potential, and so forth and so on. If you do have friction, then you're going to lose some of the energy. Okay? A typical advanced problem that I save for the assignment, it's a bungee. It's a bungee cord, right? So let's look. Yeah, yeah, yeah. And grade were good, by the way. Just have to be patient. Come on. Mhm. Let's see. Energy. Bungee. Bungee jump. So here it has potential. Then it goes to kinetic until it starts to stretch. Then it will go to elastic potential. So it's going to switch back and forth between kinetic, gravitational potential, elastic, but the total amount of energy will stay the same. Okay, so if I let go here, it has potential, goes to kinetic, and then start to stretch. So now you have elastic, everything is elastic here. Then it's going back, then it goes to potential, totally potential, no kinetic, no elastic. Then it starts to fall, so kinetic, then elastic again, and then all the way down, it's all elastic if you take the reference level there. Okay, so what is interesting is that, again, you can imagine energy as a reservoir. It's going to swing back and forth between the different form of energy, elastic, gravitational energy, or kinetic energy, but the total amount stays the same. Now, if I introduce some air resistance, you see that some of the energy is going to be lost. You see the total level is decreasing, decreasing, decreasing because you are losing to friction, right? It's a nice demo. Okay, so example here, you see, you start with elastic potential energy, okay, elastic potential energy, and then everything goes to kinetic energy. It's a conservative force, okay, because that spring force derived from the potential. So you always get back the energy. Nothing is lost in that case. So let's do something easy. So you start from, so this is a squeezed spring. So the spring here is squeezed. This is the rest length when it's not being squeezed. So you squeeze the spring. So you are doing work. So energy is being stored, which is elastic potential energy, and then you let go. And then it's going to go into kinetic energy, and then it will go to potential energy, and then it will stop. And let's say there is no friction. So you want to find that distance here. Okay, so it's easy. So you go, 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 go. Okay, so try to do it. It's easy. Don't stare. Less you stare, easier will be the homework. So total energy before, okay, I'm gonna make your reservoir. So it's everything is potential energy elastic. And then Then it's going to go to kinetic energy. Okay. When it's here, it's all kinetic energy. The spring is not compressed anymore. And then all that will go to potential energy, but gravitational. So before you're going to have 1/2 K x by which it's being compressed. So it's going to be 0.1 square equals the potential energy here, gravitational, is mgh, right? So it's going to be mgh. That's what we want to find, because if you have h, then you have d. Yes? Okay, so you can do it. You goes bye-bye here. H. Oh, you don't need a calculator, right? 0.1 square is 1/100. I forgot. What do you get? 0. Yes, so divide by 100 and then divide by 10. Did you get that? Which is 72.5 centimeters. Okay, so that's easy. That's the easy part. And then they want to find G. Okay, so you're gonna use trigonometry, and we want to use sine. So sine 30 equals opposite, which is 0.625 over d. So d equals, you cross multiply, divide. Sine 30, I think it's 0.5, right? It's 1.25 meters. Okay, is that clear? Now, you have a different way to do it. You could have said that all that energy is going to be taken away by the work done by gravity. And gravity is doing the work mg sine times d. So all that energy that you had to begin with goes into the work done by gravity. It's gravity who takes the energy away. And you will get the same thing. Okay? You're doing it? You see, you are tired too. I bet you are in bad mood too. Everyone, we good? Question? No question? Good. If we have no question, we keep going. Number B. So number B, now we want to consider step 1. So everything is compressed. Step 2, it's going to be halfway. Not halfway, but half the height. So it has a speed now. So now you have some potential energy and some kinetic energy. So you have 1/2, 625, still the same thing, 0.1 square equals, now you have some kinetic energy, mass is 0.5 v square, plus potential energy, which is 0.5, 10, and the height is 0.625 divided by 2. Any question? It's easy, right? You go from elastic potential energy, and then on the way, it's going to be kinetic energy plus potential energy. So you start from elastic here. To begin with, you have the same reservoir because there is no friction. So some of it will be gravitational potential energy and some of it will be kinetic energy, but the total amount will stay the same. Agree? right? You can say bye bye, bye bye, hasta vista, bye. So you can isolate V. The speed. Do it, do it, do it. Don't stare. I see people staring. Don't stare. Do it. And you should get 2.5 meter per second. So make sure you do it. 625 divided by 100, enter, minus 6.25 divided by 2, enter, and then you divide by 0.5. That's what you should get. Okay? So it's easy, and it's called conservation of energy. It's one of the fundamental law of conservation. Conservation of energy, conservation of matter, conservation of electric charge, conservation of momentum. Okay. Okay, we did that. Yay. Okay, so that's the idea, right? Typical problem. In physics, you start with elastic potential energy, goes to kinetic, and then goes to potential. You see, but the total amount of energy of the system stays the same. And then I don't know if I want to do this 130. Yes, let's do this one. Okay, do it, do it, do it now. Don't stare. Do it. You know how to do it. Oh, it's an easy one. It's an easy one. So you start with kinetic energy in that case. It's like a projectile. Okay, and then it's going to kick the spring, and the spring is going to be compressed. So all that kinetic energy is going to turn into elastic potential energy. Okay, 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 do it, do it, do it, do it, do it, do it, do it. It's easy, 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 it's easy, it's easy, it's easy. By the way, it's going to be the test number 3, okay? So we are reviewing for test number 3. Okay, let's do it, let's do it. So before, it has only kinetic energy. There is no friction. It's going to get to here, okay? And then what's going to happen, the spring, it's going to be compressed. Another email. So this here, the spring is happy, and now it's not happy because it's being compressed. And the distance by which it's compressed is called d. So this is a happy spring. This is not a happy spring. There will be a restoring force. It's not happy. So all that kinetic energy goes into elastic potential energy. Okay? Yes? It's easy, right? So 1/2 kinetic energy, the mass 0.4, the speed 0.5 square equals elastic. So 1/2, the spring constant is 750, and d square. Yes, yes, yes. It goes bye-bye. So what do you get? Pum 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 pum. So what do you get? Do it, do it, do it. Get a calculator. Do it. 0.4. 0. What? 1, 5. Right? So 1, 2. So that 1.15 centimeters. Okay? So now what happens if you have kinetic friction? Once it's touching. So this is frictionless, and what does it say? Oh no, there is friction now. So now there is friction, right? So because there is friction, the friction is taking away some energy. So you have some kinetic friction here. Okay? And the force of friction is the coefficient times the normal force. Okay, so kinetic friction is constant, so it's going to be 0.1, and the normal force in that case equals to the weight, right? So you have the normal force and you have the weight. So mg. So that's going to be the kinetic friction. So 0.1 times 0.4 times 10. Okay, so that will be kinetic friction. Now you have kinetic friction. So what's happening? So you start with some kinetic. Okay, you start with kinetic friction. But some of that energy is going to be lost. Okay, here it's going to be lost to heat. So this will be lost because of friction. So that will be the work done by friction, that will be negative. And at the end, what will be left will be elastic potential energy when it stops. So you start from kinetic, but the reservoir, okay, is losing some energy, is losing some liquid. Okay, so that will be equals to the work done by friction. And at the end, you are left with elastic potential. So one way you can do it, you can say, okay, I start here with kinetic. So 1/2 the mass and then the speed square minus the work done by friction, because work is energy in transfer. How much work is taken away by friction? So it will be the frictional force is 0.4. Okay, so it will be 0.4 times the distance, right? Okay, the work done is the force times the distance. That will be equals to 1/2 K and then G square. And then either you know how to use your TI or you don't know. I'm not going to do it. This is a quadratic equation. It's a quadratic equation. You see, you have like, you can multiply by 2 everything. So you're gonna have 750 x squared, and then you have minus 0.4. No, d is here, so plus 0.4 d minus no, it's multiplied by 2. So anyway, it's math, right? It's a quadratic equation, but usually you have a multiple choice, so you plug d and you see which one will work. Or you can use a quadratic formula, or you use your TI, or you ask YouTube how to use your TI to solve the quadratic equation. So it's not there. I don't have the solution. So you just have to solve the quadratic equation. An equation, you understand that it's a quadratic equation in x squared and x, right? So you need to use your TI. So you can do it on your own. You ask ChatGPT. Okay, because I don't want to do math. Okay, so that's very, very interesting. We'll go back to this one. So you have two types of forces. You have conservative forces. They all derive from potential energy. That means that potential energy depends on the configuration, and that force is a restoring force. And you can always get back that energy. And then you have non-conservative force that will be friction and resistance, and you cannot get back the energy. It's lost to heat. Or sometimes you have also non-conservative force, like when you are doing work. When you are burning fuel, it's non-conservative because there is no restoring force. Okay, so non-conservative force. If you have friction, you will go something like this. Okay, you have potential plus kinetic, take away the work done by friction, and then you have the final energy. If you put energy into the system, then you will say initial potential energy plus initial kinetic energy plus the work done on the system that you are transferring into the reservoir, and that will be equal to the final mechanical energy. Is that clear? So if you think of a reservoir, that will be not too hard. If there is friction, it does matter. The path you take does matter. If you go from A to B to C to D, you're going to lose more energy to heat than if you just go from A to D. Okay? So if you have air resistance, can we say potential equals kinetic in that case? No, very good, right? Because we don't know how much was lost. Okay, so let's try to do this one. The first one is easy. So this one is easy. The first one is easy, and then we're going to introduce some friction. So the first part is very easy. It's so easy, I'm not sure if I want to do it. So here it has just potential energy, and then it's going to slide, goes into kinetic. Okay, so potential energy is going to do M, G, H equals to kinetic 0.5, mass, and the speed square. So in this situation, it's like free fall. And you remember in free fall, the mass does not matter. So that's why the mass goes away. And you get the famous equation 2g and then h, right? So the speed is the square root of square root of 10. Thank you. Square root of 10, which is a 3 something, right? Agree? Okay, so this one is easy. So the answer is 3.1. So what's going to happen now if you have kinetic friction? And so the kinetic friction now, you're going to have kinetic friction. So the work done by kinetic friction is just the force times the distance, not the displacement, the distance. And the thing that you have to remember that I told you to memorize is that the normal force is mg cosine when you have a slope. And the component of the weight is mg sine. So you don't have to think each time you deal with an inclined plane. You need to memorize that the normal force is, in that case, it's not always the case, but the component of the weight, perpendicular to the slope is mg cosine. And here you don't have push or you don't have pull. Yes.
So when you talk about weight, are you talking about the x component or the y?
So you have the weight here, and remember that the component of the weight here is mg cosine, and the component of the weight here is mg sine. Nothing new under the sun. We've done that many times. So it's going to go down. So that will be my x-axis. That's going to be my y-axis. Okay, so along the y, you have everything up equals everything down. So down, you're going to have the component of the weight here that I told you to memorize. So you did. See? That will be the component of the weight here, and then you have the component there. So anyway, up equals down. My point is that normal force equals mg cosine 30. Do you agree? Okay, we've done that many times. So the kinetic friction in magnitude is the coefficient times the normal force, which is mg cosine 30. Okay, so the kinetic friction is the coefficient, which is 0.15, times the mass, which is 3, times 10, times cosine 30 degrees. Okay? Okay, what else do we need? We need the distance here. So it's going down. That distance here you can find, it's going to be 1 meter, right? Because sine 30 degrees equals opposite is 0.5 over hypotenuse. So D equals 1 meters. Do you agree? I need all that before doing conservation of energy. Okay? Are we good? Okay, so what's happening? You start with potential energy, gravitational potential energy. And then some of your reservoir, okay, will be lost because friction is doing negative work. That negative work will be minus the kinetic friction times the distance. And at the end, you will be left with some kinetic energy. Agree? So you start with a full reservoir of potential energy, and that will be mgh, so 3 times 10 times 0.5, and then minus the work done by friction, which is this times d, which is, so the coefficient 0.15 times 3 times 10 times cosine 30 times 1. That will be equals to the kinetic energy, 1/2, 3, and v squared. Okay? So what's the equation? The gravitational potential energy that you begin with minus the work done by friction will be equals to kinetic energy at the end. And the work, by definition, is the force times the distance. And the distance is not a displacement. If it was gravity, you can put displacement. In that case, it matters. Because it's going to rub. Agree? So a typical mistake will be to forget to multiply by the distance, right? Don't forget to multiply by the distance. Another mistake will be not to be able to remember that the normal force in that case equals to the y component of the weight, mg cosine. And here you have mg sine. You could have done it a different way. You could have used the work kinetic theorem. So you could have said, okay, gravity is doing positive work. The kinetic friction is doing negative work. Then you could have said that the work done by gravity minus the work done by friction equals to the change in kinetic energy. And you will have you get the same thing. Okay, you could have used the network equals the change in kinetic energy. Okay, and the network will be the work done by gravity, which is mg sine times d, minus the work done by friction, so Fk times d equals the change in kinetic energy, and you will get the same thing. So the conservation of mechanical energy derive from that. Both will get the same thing. This is called the kinetic energy theorem. This is called conservation of mechanical energy. But in that case, you are losing to friction. Very good. Yes? And then it's just stupid math. So you multiply by 2 everywhere, and you divide by 3 everywhere, and you take the square root. And you should get here, 2.7. Okay, you can also check how they did it. Any questions? Okay, so now it's something different here. So it goes down. How far? So it goes down, and then you keep going and losing some energy. So now we went from here to there, right? So here it has some kinetic energy, and we know the speed. It's 2.7. Yes? So potential goes into heat and kinetic. At the end, it's all kinetic, and eventually it's going to stop because friction is still acting up. And they want you to find how far will it go. So it's the same kinetic friction. It's the same kinetic friction. No, not the same kinetic friction. It's the same kinetic coefficient. It's the same kinetic coefficient, and they want you to find how far will it go. Okay, so can you do it? So here the speed is 2.7 meter per second. So we start from here. That will be step number 1. And then it's gonna have some kinetic energy here. So it's the same speed. And all of a sudden it's gonna stop. Okay, so the speed is decreasing. So it's decelerating because you have net force. The net force is to the left. So here it has kinetic energy, and here it has no energy because the work done by friction. So now we have kinetic friction here. And if you do your free body diagram, you have the normal force, which is up, and you have the weight, which is down. Okay, so we have that normal force equals mg. The kinetic friction now is the coefficient times the normal force, right? So it's going to be, the coefficient is what? 0 point something, 0.15. So 0.15 times up equals down. So normal equals the weight. So 3 times 10. Okay? So the work done by friction, it's negative, right? So it's negative 0.15 times 3 times 10 times the distance. So it goes from here to there. That will be your distance. Okay? So if you want to do the reservoir, you start with kinetic energy, and then little by little, everything is lost to heat. Okay, so you start with kinetic energy, so 1/2 the mass, the speed, and then kinetic friction takes everything away. So 0.15 times 3 times 10 times d, and at the end, nothing is left. And you can solve for d. Is that clear? So think of a reservoir. Everything has been transferred. Work means transfer, and work is force times distance. Work is heat. Heat is also energy in transfer. Any question? And you should find that the answer is 2.5 meters. And here it says textbook 7.5, 7.6, so you should do 7.5, 7.6 on your own. Yes.
So when there's heat, kinetic energy is going to be 0.
It depends on the problem. When there is heat, that means there is a minus. So if there is heat, that means whatever you begin with, so it could be potential plus kinetic plus elastic potential, you have to take away minus the work done by friction. So that will be minus friction times the distance. Here it should not be, that's a typo. It should be saying distance. That will be equals to the final energy. So if they tell you it stops, so then yes, the final speed will be equals to 0. There is no kinetic energy, but it depends on the problem. And if you put work into it, okay, so maybe you are burning fuel, then it will be the work done by the fuel or the work done by you, and you add to the reservoir. You take away from the reservoir, you add to the reservoir, and that will be the final reservoir. If there is no non-conservative force, then everything, you don't add and you don't remove. Okay, and okay, so let's see. 45. Okay, so this one is also easy. I'm not going to do it. So it has, what type of energy does it have to begin with? Kinetic. And they want the maximum compression. So that will be kinetic equals to elastic. Exactly, very good, right? Elastic potential energy. If there is no friction, now if there is friction, then you have to find the work done by friction. So if there is friction, then you have to say initial, that will be in your reservoir, and then you take away some of the energy because of the work done by friction, that will be K times X, so the frictional force times X, so that will be the work done by friction is taking away, that will be at the end 1/2 K X squared. And that will be the same X. This is because here there is no friction, no friction, no friction. And then friction starts only when you touches the spring. So when the spring starts to be compressed, you have friction. Okay, so you start with kinetic energy, and then you touch the spring. So you have some work here, and what will be left is elastic potential energy. So why is it a headache? Because again, you're going to have a quadratic equation. So again, you have to use your TI, and remember how to use your TI. You see, that will be the quadratic equation. It's a good problem for you to make sure you know how to use your TI, and you have the solution here. Okay? So this one goes on the other side. So kinetic energy minus the work done by friction equals elastic potential energy. So they use a different approach, but the same idea. Here you have textbook problems to do on your own. Is that clear? That's good. So think about this one. So we can take the whole thing in like the whole system. So we talk about conservation of energy, that will be the whole system. So you see here, you take the whole system and the spring is not compressed. So it's happy. It's not squeezed. It's happy. It's not stretched. It's happy. But if you take in account the whole system, what type of energy does it have to begin with before you let go? The whole system. Like M1 has no energy to begin with. Does M2 has energy to begin with? Exactly, gravitational potential energy. Okay, so to begin with, you have gravitational potential energy. And then it's going to fall. Okay, and all that gravitational potential energy is going to go into elastic potential energy because of the spring. Does it make sense? So it's the whole system. When we talk about conservation of energy, conservation of momentum, is the whole system. And the spring is going to be stretched by h. So just write down the equation. Just write down the equation. We are not going to solve it, but just write down the equation to make sure we know how to do it. So the only energy to begin with will be potential, gravitational potential energy. So that will be M2 GH. This one is not moving, it's not being stretched, it's not being compressed. That will go. So we have to decide that the potential energy equals 0 here. I need a reference level, right? Reference level. That goes to elastic potential energy in there. So that will be 1/2 K H. This is a K. X squared. Okay. We wait for the system to stop. So potential energy goes into elastic potential energy. Yes?
The spring is being stretched, right?
Yes.
Oh.
Stretch. So here it's not stretch. And then this one is going to fall. So it's going to pull on that, right? So it's going to be stretched. It's going to do something like this. And it's going to stop here. Okay? Now, if you do have kinetic friction on the way, then you have to do M2GH minus the work done by friction. So will be the coefficient times the normal force. If you have friction here, so you have the normal force here and you have the weight. So normal force will be M1G times the distance. So it's moving by h. That will be 1/2 kh squared. If you have friction. So don't forget that to find the friction, you need to find the normal force. So you have to go up equals down. And we suppose here there is no friction because it doesn't touch. So the only friction involved will be between M1 and the surface. Okay? Oh, you have elastic to kinetic. You see, this is elastic, 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 potential, elastic. How smart is that? And that was all over, Marina. You see what they do? We did that problem together, right? You have potential kinetic force times distance. Potential kinetic force times distance. So if you have a small distance, you can have a huge force. And that force will be equal to the normal force. And you have to take away the kinetic, the work done by kinetic, right? Okay. Okay, so you can oh, they were asking for the coefficient of friction. You see, but they have the same equation, right? So you start with uh, potential energy, M2GH, that will go into elastic potential energy minus the work done by friction. Any question? Okay, application, escape velocity. So if you want to escape the Earth, the computation is quite simple. So if you remember the gravitational potential energy of a mass on Earth, it's going to be negative because it's binding. Okay, remember we took the force and you can integrate and we get the gravitational potential energy of a mass on Earth. So you cannot escape because it's negative. But now if you give it some kinetic energy because you are burning fuel, you want to give it enough kinetic energy such as when it reaches infinity, so very, very far away, at least it's going to stop and it's not going to have any more gravitational potential energy. So at infinity, very, very far away, it has no more energy. Stop from moving, but it's kept the Earth. And if you do that, you know the math is very easy. And you can see that if you want to escape the Earth, that will be the velocity that will be about 7 miles per second to escape Earth, to escape gravitational field. Is that clear? It's easy. We can do the same thing for a black hole. Similar equation. Okay, so let's go to something very fun. Let's go back. So we want, so the idea is to know exactly how high you have to place the block to make sure to make the loop. So it doesn't become the loop of the doom, right? So it's a loopy loop. So you want to find the minimum height to make sure make it around. Okay, so you're gonna have to use two equations. First equation will be conservation of energy between here and there. And also, remember, you want to find the centripetal force that was from the test, right? Centripetal force is toward the center. You have the weight and you have the normal force. And if the normal force equals 0, you start to go off tangent. Okay, so try to do that. Write down the equation, first of all. And I have a video, but I don't know where it is. So do it. Don't wait. Cannot find it. Look.
A basic conservation of
Maybe it's this one. We'll see. So anyway, let's go here. Let's do it. Write down the conservation of energy. So you want to find the minimum height so it make the loopy loop. So this is R. Here you have R. And you want to find this height to make sure that it's gonna make it. So it doesn't fall. And remember, we have something upside down. That was the test, right? And you have a force. You have mg here, which is down. And the normal force is always from the surface to the car here, which is down. Okay? So if we look at the centripetal force, we have that N, the normal force, plus mg equals mv squared over r. So that was the test, right? And before, just as it's gonna, lose contact. So if it's losing contact, so it goes along a projectile motion there. So in that case, m equals 0. So that means that the minimum speed that you get is rg. So you have this equation here from the test. Do you remember that? Okay, so it means you need at least your speed to be equals to rg, the square root of rg, otherwise off tangent you go. Like the guy, by the way, I checked and he's fine. It's from South Africa. Otherwise you're gonna go something like this. So that will be your first equation. Second equation, you're gonna have what kind of energy does it have here? Yes, right, so it's gonna be mgh. There, it's not going to stop, right? So it has some kinetic energy plus potential energy, right? So it's going to be mg and then 2r. So you have two equations with two unknowns. Agree? Okay, so you have gh equals 1/2 v square is given by equation 1, so rg plus 2rg. So let's say it goes bye-bye. Bye-bye. Nice to meet you. Bye-bye. So h will be 2r plus r over 2. So that will be 5r over 2. Which is 2.5 r. So it means that distance here, so this is 2, this is 2r, and right, 2.5, and that will be r over 2. If you don't do that, it will not make it. So usually I used to have a demo with a loopy loop to show that if you place it here, it's not going to make it. It has to be at least 2.5 R. Yes?
Oh,
Yes.
how? Get the vertical equation. The v squared is
But that's the centripetal force from test number 2. Centripetal force equals the normal plus the weight. If it's about to lose contact, normal force equals 0, so we get that. Okay, so that's the previous unit. Okay, remember it was in the test. It's a centripetal force. Okay, So the centripetal force in that case is provided by the normal and the weight. If it's about to lose contact, like the guy, and then normal force equals 0. So that's how we find the minimum speed. This is your minimum speed. You can go faster, but that will be the minimum speed. The minimum speed will be this. So it doesn't become loop the doom the loop, or whatever it was called. So minimum speed to make it. Okay? And there is a great demo, but I cannot find it, so I don't know.
And the reason for that is because if we start the marble down here, then its starting energy is not even high enough. Here it only has potential when I release it. There's not even enough potential energy to make it to the top of the loop. Let's make it around the circle. If we go to the next most obviously guessed point, which is the same height as the top of the loop, it gets closer, but still doesn't make it around the circle. As this starts to move, it doesn't just slide down the rails, it's also going to be rotating as it moves. So the point that we need to release the ball is where the potential energy is going to equal the potential energy top of the loop, plus the kinetic energy at the top of the loop, plus the rotational energy at the top of the loop. This is approximately the point on the rail. It's the marble. When we release it from there, it makes it around the loop. But if we release it, it stops making contact with the ramp here. It takes a little skip. When it all boils down, what we're looking at is conservation of energy.
Because so that's a different approach, right? But it comes to the same thing. So it takes in account rotational energy, but it's the same thing. Okay, so let's open a new unit, and this is called, it's fun. That's easy, kind of easy, up to a point. It's called the conservation of momentum. Okay, so first, let's define a new physical quantity, P. Okay, it's a vector, and this is called momentum. So it's going to be the mass times the velocity. So momentum can be into the mass, or it could be into the velocity, or both. So that was defined by Newton, and Newton called it quantity of motion. So if there is momentum, then you can kick. Okay, if there is a kick, then there is momentum. So kick equals to the change in momentum. Okay, so that was called quantity of motion, and it's a vector, so it will be in the same direction as the velocity. So the unit for momentum is kilogram meter per second. Agree? Okay, so, and because it's a vector, then it's going to be along the x component. It has a x component, it will have a y component, and it will have a z component. Unit is mass, kilogram, speed, meter per second. So it has a direction. For now, we're going to focus on 1D. So momentum can be positive if it's moving to the right, negative if it's moving to the left. Okay, so Newton, when we talk about Newton's second law, F equals ma, in his book Principia, he didn't write it this way. He didn't write it this way. So I'm going to rewrite the equation. I'm not going to use in derivative. Let's say just delta V over delta t. So you multiply by the time both sides, you're going to have F delta t equals m delta v. And that's how Newton wrote his Newton's second law in his book. And it has a lot of meaning. You can see through that equation because it means if you apply a force during a time t, the velocity will change, meaning speeding up, slowing down, or turning, but it depends on inertia. How much it will change depends on inertia. And the second thing you can see is that you need two things. You need a force and you need a time. So for the same change, m delta v, okay, for the same, so let's define those terms here. So that term here will be equals to what? So P equals mv. So if you have m delta v, what do you think this is? Very good, delta P, right? It's a change in momentum. That will be a change in momentum, delta P. Just for those who forget, final change is a final minus initial, and the final velocity minus initial velocity. That's the meaning of a change. So this here is the change in momentum. This here, so it depends on the textbook, but sometimes it's called J, or sometimes it's called I. But anyway, it's called the impulse. Impulse is a kick. And the impulse depends on the force of contact and the time. The force of impact and the time of impact. So if there is a kick, there is a change in momentum. If there is a change in momentum, there is a kick. Okay? So the impulse equals the change in momentum. Unit of impulse is Newton second. Change in momentum is kilogram meter per second. It's going to be the same thing. Okay? Because the force is mass times acceleration. So it's just a different way to write Newton's second law. Now, if I use calculus, okay, if I use calculus, so you have here delta P equals F, okay, or I can say delta P over delta T equals the force. Now, if I use calculus, the delta becomes a derivative. So if you take the derivative of the momentum as a function of time, that will be equals to the force relative to time. Okay? Okay, so impulse, that will be the definition, is force times time. Okay? So a lot of application in sport, because for example, when you're gonna hit a tennis ball, you don't just kick quickly, right? Because you cannot increase your force. Okay, you cannot increase the force. So, but to increase the momentum, what is it that you can increase? The time. You're gonna follow through. If you want to increase the momentum, to make it very hard for your partner to catch the ball, you want the ball to go as fast as possible. So because you don't take anything non-legit, right? You cannot increase your muscles, so increase the time of impact. By increasing the time of impact, you're going to increase the momentum, so you're going to follow through. Same thing with baseball. Not like I play baseball, but if you have the thing in your hand, you're gonna follow through to increase the speed. Does it make sense? Okay. So if there is a kick, there is a change in momentum, you want to follow through to increase the momentum. So let's do this one. It's super easy, extra easy, plugging in, nothing special. So easy, I'm ashamed to ask you to do it. So such easy. So force times time is 5 milliseconds, so 0.005123 equals mass is 0.06. Final final is 40. Okay, it's given final speed, and you start from 0 speed. You start from rest and you follow through. Okay, so the force will be Newton. So if there is a kick, there is a change in momentum, but you can play on the force or you can play the time. If you increase the time, you increase the momentum. Okay. You can increase the force also by decreasing the time, right? You can say the force equals m delta v of the momentum over the time. So if the time is small, the force will be huge. So there is something called a jab in boxing. You know, boxing here. It has to be very quick, quicker, more force, right? It's not like the cross. The cross is more power. So anyway, 480 Newton. Okay, so now the real equation is actually the average force. Because if there is a kick, the kick doesn't have a constant value rho, right? It starts to be small and then it increases and then it's going to decrease. So the real equation is the impulse will be equals to the average force times the time. If you apply a force over a time t, there will be a change in momentum. If there is a change in momentum, there will be a force times time. Is that clear? So you can do the math here, you can do the calculus, and that's what you will get. That will be the real equation for impulse. You need to integrate the force over the time, and you get the average force because the force is going to increase and then decrease. Okay, check. Yes. Okay. Okay, so again, this is called the impulse momentum theorem. So the net force times the time equals the change in momentum. Do you agree? It's easy, right? You apply a force over a time t, the velocity will change. By how much depends on the mass. So for example, in boxing again, for the same change in momentum, let's say someone is knocked on the floor, okay? If he doesn't want to get too much impact, what's the trick? Do you stay stiff or you gonna roll over? Roll over. You want to roll over. Very good, right? So typical conceptual question. By increasing the time of impact, you're gonna decrease the force. So you roll over. Like it's easy to remember. Shit, someone is punching me. Okay, let's roll over. But in theory, I guess it takes practice, right? That will not be a good idea because you decrease the time and you increase the force. That's the idea of a jab. Boom, boom. Okay, that means the time is very small, the force will be huge. Now the cross, for those who like boxing, the cross is because you want to have a very large change in momentum to provide a large kick. So when you're gonna do the cross, you put all your body. It's not just your glove. You put all the body into it, right? So the change in momentum will be huge because it's all your body that goes into. So the kick will be large. So think of change in momentum. It's a kick, right? Impulse. They call that an impulse, but it's easier to understand if you call it a kick. So it's all physics, right? So if you want, of course, if you rather be stopped by a wall of brick or a hay stack, that will be the haystack, right? Because you increase the time, you decrease the force for the same change in momentum because you're going to stop. So same way, if you jump, do you stay stiff or do you bend the knee? Bend the knees, right? So you increase the time of impact, you decrease the force of impact. If something bounces, there is always a larger change in momentum. So you can take those two examples here. You have the teddy bear and then stop there. And then you have a bouncing ball. So the change in momentum for the teddy bear will be the mass. Let's say they have the same mass. Final speed is 0, minus initial speed is minus v because it's going down. So the change in momentum is mv. But for the bouncing ball, it's going to be worse, right? The change in momentum will be equals to final minus initial, which is twice as much. Okay, so the change in momentum will be worse for this one than for that one. Because not only you need to stop, but you need to reverse the motion. So when two things collide, it's always worse for the one that is bouncing off. Okay. I don't know why we are supposed to do this one. Okay, let's do that one. Well, it's easy. It's bouncing off. Bouncing off is always very bad. Impulse. So impulse by definition is the mass times the change in velocity. And here we have to be very careful because velocity is a vector, so it has a direction. Okay, so J will be the mass, so 1, 2, 3. The final is positive here. Okay, 2.6 minus initial is negative. Okay, that will be a typical mistake students will do. They forget about the direction. Okay? So, you see, when I was teaching math, I would say the enemy of my enemy is my friend. So that's a plus, right? So J equals 1500 2.6 plus 15. It's a big number.
No.
Yeah.
Not 26. 264.
See, 26,000, no? Right?
1.5
Yeah.
I misplaced the 0.
1, 2, 3. And the average, so average times time, average force times equals the impulse. And the time is 0.5 seconds. So it's going to be 26400 divided by 0.15. Okay, so smaller is the force, the smaller is the time, larger is the force of impact. That's why you have airbag. If you increase the time of impact, you decrease the force. Okay? Okay. A lot of application. We'll go back to that. We still have a few minutes. So this is very interesting story, 19th century during the gold rush. And I don't know if I told you that, but they say it's when there is a boom, like let's say crypto, for example, or solar panels, it's better to support the economy than just to go with the economy. When people were starting to mine crypto, the people who really made a lot of money, they are the one who made or were selling the graphing cards, right? That they use for the gaming laptop. So in the story of the 19th century, there was a gold rush. The people who made the most money, they are not the miners. They are not the one who were mining for gold. They were the one who were selling hardwares. They were the one who were selling shovels. They were the one who were buying land and selling land. They are the one who were selling jeans. You know, Levi Strauss. That's how they made their fortune. They came up with jeans that were very, very tough, right? Very sturdy, could not be ripped off. That's how they made the fortune. So there is this guy, his first name Lester Pelton, and he got the idea. So when you are mining, you need a water wheel, like a mill, right? And before the paddle were flat, and he came with the idea to make them curved, and he patented this invention. So why is it better? Because it's bouncing off. And because it's bouncing off, you have more kick. And if you have more kick, the wheel will speed up, right? More speed. It will go at least like twice the speed, right? And he became very, very wealthy because of that. So this is called the Pelton wheel. So the idea is that if it bounces off, you have more impulse, you have more kick. Isn't that interesting? So again, when there is a boom, you don't want to go with it, you want to support it. You want to sell graphing cards when everyone is mining for Bitcoin, for example. You will make more money. That's the idea, right? And so that's how. There is another example. There is James Lick. I don't know if you heard of him. He made a fortune in California because at the time San Francisco, the land were for nothing. So he bought a lot of land. He waited and then he sold them back. So he became very, very wealthy. So anyway, that's for the story.